Only error recovery I will have to do. Error recovery in Yak is not done in the lab also. Okay, so yeah, we'll start with the class today. And many of you have not filled that form. I see only 6-7 responses.
Can you keep it open for a couple more days?
Couple more days. Okay. By this weekend?
Yes, ma'am.
Yeah. Okay, so in the last class we had discussed about the Boolean expression, and we took an example also how to generate the intermediate code, how the labels are getting generated. You would have seen that if I have something like this, S gives if B S1. Okay, so Boolean values and jumping codes. Boolean values we have to, I have already told you that two main things why Boolean expressions are getting used. One is to evaluate to alter the flow of control. The other thing is to evaluate the Boolean expression itself. Like if I have something like B is equal to x less than y and something x not equal to y or something like that, it will evaluate to true or false, but B will have either 1 or 0 value getting assigned, right? So these are the two main important things why Boolean expression is getting used. So when we are generating the code, the when we are handling both the roles of these Boolean expressions, a clean way to handle them is to build a syntax tree for expressions first, and using the two approaches are there, using them to generate the three-address code for the Boolean expressions. So one method in which we do two passes. What we do is we construct a complex syntax tree, and then you traverse the tree to evaluate the Boolean expression. Okay. First approach is to use two passes to evaluate the Boolean expression. One is to construct the syntax tree, one pass. The other pass is to traverse it in some order, depth first search or BFS or something. Some traverser order, traverse it in some order to evaluate the expression. The other one is use one pass for statements, okay, and two passes for Boolean expressions. So if I have a statement like if B S1, I have to evaluate B, and based on whether it is true or false, I may have to jump over S1. So when I'm evaluating B, I should know S1. I should have generated the code for S1 already. Okay, in the first pass, what it could do is it can construct the tree for B and for S1. Then I would have got the S1's code. Okay, so I know where this is ending, and S.next label would have already been generated. Then you traverse this B to evaluate the value of true or false. Okay, based on true and false, you jump to S.next or to S1's code. So two passes for B and one for S1. This is one more method in which you can, go about the evaluation of Boolean expressions. This is useful when you have something like assignment statement, as I told you, just a Boolean expression evaluation, wherein you construct the pass tree and traverse it in some order to get it evaluated, because we have to cover both. One, both the use of Boolean expressions, one for the alter the flow of control, and the other one is to evaluate the Boolean expression. So either of the methods we have to use. Okay. So what happens if I use two passes? Right, it will take I have when I'm evaluating B, I would have already created S1, so I need to have two passes for B and one pass for S1. It will take more time for me. Time consumption is more, right, because I have to do two passes. So if I have to do it in one pass, what is the problem if I have to do this in one pass? Why can't I do it, or how can I do it? What could be the problems if I have to do all these things in one pass? Because I'm not traversing the B again for true and false values. Construction and parsing should happen at the same time, only in one pass. What could be the problem? Think. What could be the problem if I do it in one pass? The issues. Anyone? To understand backpassing, you should know the problem. Do you see any problem if I have to do it in one pass? Why I have to do two passes for the expressions? Hmm? No one. Sridhar?
No idea.
No idea. So if you have to do it in one pass, you should know the target, right? The bees could see this will start from left. So when you're constructing the bees and you're traversing to decide on B and true false values, if suppose it turns out to be false, then you have to jump to S dot next. For that, S's code should have already been there, but you are there in B. S is not yet reached. So S's code is not yet created. If you have to do it in one pass, you should know the target of the jump. The label would have not been generated, right? Because I don't know the S's code where that S1 will end. This has not yet been generated only. So that is the problem. So this problem, but it is efficient with respect to time. You need only one pass to complete the 3 address code generation for this statement. To facilitate this kind, we have backpatching. Okay, in backpatching, what we do is we generate the go-tos, like how we do it for the semantic rules, using semantic rules, right? Go to only the problem is we don't know the target of the jump. That label is left blank, and then it is filled later when SS code is generated. Okay, that is called as backpatching. Okay, understood why we need backpatching? If you have to do everything in one pass, both B's code generation and evaluation, S's code generation, you have to use backpatch to do it in one pass. Otherwise, it requires two passes. One pass for S1 code and two passes for the expression. One to construct the tree and then traverse it. Okay, so we'll see backpatching, how to apply backpatching to generate the 3 address code for this. For that, the Boolean expression, we had discussed the semantic rules, right? We will do some modification to that semantic rule so that it accommodates this backpatching. Okay. So when it is generating the goto, it will leave the true and the false labels blank, and then it will fill up those blank spaces once S's code is generated. Okay, we'll see that how it does it. Because both construction and evaluation of B should happen in one pass here. Okay. So in this, what it does in backpatching, it maintains a list. Okay, two lists it will maintain, one for the true list and one for the false list. So that list will contain all the targets. It has to fill it up whenever B evaluates to true. Okay, what are all the possible jumps? It makes a list of that, and then it selects from there. Okay, so what we do is in backpatching, when a jump is generated, the target of the jump, is left blank. Okay, left temporarily, it is left blank. So each jump is put on a list of jumps whose labels are to be filled in whenever the proper label can be determined. Okay, so here we maintain a true list and a false list. Okay, true list for a non-terminal B is nothing but it is the list of all the labels to which we have to jump if B is evaluated to be true. Okay, false list for a expression, Boolean expression B is nothing but it is a list of labels or false labels to which we have to jump if the B is evaluated to be false. It's like an attribute which we associate with the B node. Okay, to manipulate this list, because we may have, if B is composed of many other B's like this, if it is again composed of right? Every time it won't be even relational operator E2. It can composed of another two B's, and at every node I will get a true and a false, right? Because we evaluate true and false. So every time this B's trueness is depending on this B and this B's trueness, right? So we maintain a list here and we keep on merging them, because here also have to create true and false. Instead of having one single label, here it will be a list, because I don't know exactly where it is going to jump. That's why I'm creating a list out of this. So this true list will have all the true targets, and false list will have all the false targets, which is depending on this B's trueness and this B's trueness, falseness and falseness. Again, this is depending on this B's trueness and this B's trueness or falseness or falseness. So I have to generate those lists everywhere whenever I have a node B, right? So to manipulate this list, we have three functions. Okay, so three functions are used. You make a note of this, because when we are writing the semantic rules, we need these functions to manipulate. The first one is I have to make a list. I need to have a method which creates this list, right? So make list of I. This is nothing but it creates a new list containing only I. Okay, what is this I? It is an index to the array of instructions. Okay, it returns a pointer to the newly created list. Okay, this is what make list function will do. It will create a new list which is containing only I, which is nothing but the index to the array of instructions. Okay, then next function is merge p1 comma p2. So it concatenates the list, because I told you, this b can depend on the further b's. So in that case, I may have to concatenate, because when I am telling b dot true, both b1 should be true, b2 should be true, and when I'm telling b dot false, either of them can be false. Okay, to manipulate all those things, we need to have this merge function which concatenates the list pointed to by p1 comma p2 and returns the pointer to the newly created list. Okay, then third one is backpatch p comma I. So it inserts I as the target, because we would have left blank when we are generating, right? So I have to backpatch the target of the jump. So I use this backpatch function wherein I send the list and then I, which has to be I as the target label. For each of the instructions, on the list pointed to by P. Okay, so it inserts I as the target label for each of the instructions, which is targeted pointed by pointer P. Okay, these three functions we require when we are writing the semantic rule for the Boolean expression to do everything in one pass. Okay, did you make a note of this? Yes, we'll see the Boolean expression again, and what are the translation schemes which you have to apply for those Boolean expressions if you have to use backpatching. Okay, the semantic rules which change. Okay, so all of you have that grammar, right? The Boolean expression grammar. We have to see one by one, or, and, not, even, relational operator, E2. All those things you have to see it again with respect to backpatching now. So we start with the first one, B1 or M B2. So the use of M here is just to have the semantic action to pick up, okay? Just to indicate the next semantic action to pick up and at appropriate times. So it will have the next instructions address. So if B1 is turned out to be false, I have to evaluate B2, right? B2 is address M will have, okay? So M is just a marker non-terminal in the grammar which causes the semantic action to pick up at appropriate times. Appropriate times in the sense when B1 evaluates to false, M will be called to have the next instruction to be executed, the address where it has to jump to. Okay, so that is indicated by
M contains B2's address.
B2's address. So
Yes.
whenever we are inserting this non-terminal to make my grammar looks the same, I should not change the existing grammar. So I will have to include M giving epsilon as the production in the given grammar for Boolean expression. Okay, this is one extra non-terminal and the production which will be there in the grammar for B. With the B, this one, B1 or MB2, like that. B1 and MB2. So this whole B grammar will be there. With that, M is a new non-terminal which will produce only epsilon so that your initial grammar remains the same. So we'll see the semantic actions associated with this. I forgot to write. B. B gives B1 or M B2. Okay. Now, when I have to execute B2, when I need a backpatching here, just go through the functions here. Okay. When I have to backpatch, call the backpatch, on which list? If B1 is true, then should I execute B2? See, for every B here, likewise how we did for Boolean expressions. Boolean expressions, you just refer back. We had to write B dot true, B dot false. We manipulate B dot true, B dot false, and B code, right? And B1 true, B1 false, B2 true, B2 false, and B2 dot code. Likewise, here also, what you have to do is always you have to check backpatching is required or not. If backpatching is required, backpatching will be called first, and then we have to manipulate B dot true list and B dot false list. Now we have to manipulate the lists using the functions, three of the functions. So for the first one, I will just give you. So B1 dot false list, comma, M dot instruction. So what we are doing here, backpatch P comma I means what? Inserts I as the target label for each of the instructions on the list pointed to by P. Now this is P and this is I. Okay, so what did I say? What is M? M will have the next B2's address, right? So that is the target of the jump. When B1 is false, I have to evaluate B2, right? Then only I can say B is true or false. So B1 dot false list. So this is false list. The target of false list should be M instruction. That is the target. Understood? So whatever is there in this list, B1's false list, the target jump of the target, that is B2's address, will be patched, inserted to all the B1 dot false list instructions. Okay. Now once I patch it, now I'm ready to write B dot true list and B dot false list. So when I say, how do I create B dot true list? It can be B1 dot true list, or it can be B2 dot true list, because I don't know which one will become true, right? So I'll have to call the merge. Okay. If B1 dot true list is true, then I will attach that B1 true list to B2 true list. If B2 is turned out to be true when the control is flowing at the runtime, so B2 true list will be given to B dot true list. So I will call the merge, which will concatenate both the lists and it will assign to B dot true list. Now, what should I write for B dot false list? Check the functions.
Merge B1 dot false list, B2 dot false list.
Is it? Check. When will you call merge? When will you call merge?
When we concatenate two lists and then return a pointer to the newly created.
Correct. But when should I call merge? Either B1 or B2. If one of them is true, then I can say B is true. That time I will call the merge because one of them can be true. But when I say B dot false list, I'm certainly knowing that when B will become false. When B will become false? When B2 is false, right? So B2's false list will become B's false list. I need not call merge there. When you call merge, B1 false or B2 false should make B false. That is not the case. If B1 is false, there is a chance of B2 to become true, right? So B dot false list is nothing but B2's false list straight away.
Ma'am, then why did we merge? Okay, fine. Yes, got it.
Okay, because if I say B dot false list is B1 dot false list, that is not true. Because if this is false, I have to check for B2. That's why I'm doing backpatching on B1's false list. Okay, but merge on true because B1 or B2 it is. So B1 true list or B2 true list. If one of them is there, then B will become true. Okay, this is how you do it. Now I want you to try for B1 and MB2. All of you try. Second one is, sorry, B1 and MB2. Now backpatch I have to call in what?
Backpatch B1 dot true.
B1 dot true list.
True list.
Yeah.
M dot instance.
Yes. Okay. And then B dot true list, because when B1 is true, I have to check for B2 also because there is an and here. Okay, that's why M is associated with the B2. So target of the jump should be M instruction for B1's true list. Okay. B dot true list will be when I can say straight away that B is true.
B2 dot true list.
Yes, it is B2 dot true. Then when B dot false list should contain if either
Merge B1 dot true list and B2 dot true list.
yes, false list it is.
Yes, my bad.
Okay, easy. You have to merge on either B1 can be false or B2 can be false. All right. So this is about and an MB2. The third one is B gives not of B1. Here we don't use M because it is straight away the execution of B1's code, right? Only the true list and false list values will differ. So B dot true list will be B1 dot false list, and B dot false list will be B1 dot true list. Okay. Then B gives bracket of B1. Who will tell me? Bracket of B1. B dot true list is B1 dot true list, and B dot false list is B1 dot false list. That's it. There is no manipulation here. It is straight away. Only to highlight it is a parenthesized expression. Okay. Then next we have the major thing is here even relational operator E2 wherein we generate the gotos, right? So the fifth one is B gives even relational operator E2. Okay, this is the most expression. It's we need not have M because we don't have a code here. You have to generate the code here for even relational operator E2. Even if you refer to the semantic rules which we have discussed before, it will not have the B's code. I mean the something like B dot true and B dot false, something like that. We have to generate the gotos, ifs and gotos here, right? In the B dot code. So in the same way, here also, what we do is we create the lists here, because here we have assumed that true list and the false list is already created. So somewhere in the grammar itself, I have to create the list, right? So whenever I reach to even relational operator E2, I will create the true list and the false list here at this particular point. B dot true list is equal to, I use the make list function. Make list. This is some variable which will have the number. Next instruction.
Now we don't write M or something here.
No, M dot instruction will come for this one. Here we create the list. Then M dot instruction will get created. This one will be created at M gives epsilon.
No, like won't it be written as even relog MP2 and then do back?
No.
Oh no, no.
No. No.
That's
It
only
won't.
for logical ones.
So this list should differ from this list. So I will just add the extra one to this list. This is just a number. Okay. This is just a number to differentiate between the lists. It will be more clear when we take an example and use the semantic rules to create the lists. Then we need to have this statement. Instead of generate, we use emit function here. Okay, that is the difference. If should be printed even dot address relational operator E2 dot address, that remains the same. Only difference is the target we used to give B dot true, right? Instead of that, we leave it blank. Okay, which should be backpatched later. So emit, go to, this is the false case, and we leave it blank. Okay, so this is the difference between the previous Boolean expression semantic rule and here. We used to fill it up with B dot true label and B dot false label here. Here we don't do it. Let the lists and the backpatch decide later. Okay. Then we had true and false.
What is emit?
Emit is like a generate only.
Yes.
Yeah, this is false. Blank. So B gives true. We'll have only the true list. You just create only the true list here. Next instruction. And you will have to emit, go to, this is the unconditional one, and leave the target blank. Okay, and likewise for the false. What you do, you create the false list. Make list. Next instruction. And emit, go to. Okay, that's it. This is for the true list and this is for the false list. Now, the last one is M is giving epsilon, right? So M instruction is equal to next instruction. Because this M instruction I'm using in the backpatch. I told you M will have, this will become the target, right? So after B1 I'm executing, M should have B2's address. Okay, so I'm using make list, next instruction, make list, next instruction plus one. So this will be the target. So to create the lists, which is nothing but the label on which it has to jump when B is true and when B is false. So like that, we create at M gives epsilon, we create M instruction is equal to next instruction, which is the index for the list, right? Which will become the index wherein, you use for backpatching P comma I. That I is this index itself. Okay, or if I make a note of this. So next instruction will hold the index of the next instruction to follow. right? Is that clear? We'll take the example of that and then.
Ma'am, why do we write emit go to dash for B gives false? Like we know B is giving false, so
No, we don't know the target of jump, right? So the label is not there. The label is not there. We have to call backpass to insert it. We don't know where to jump.
ma'am, but like it's B gives true, so it
Huh.
should be.
But we don't know the targets, no, which is there on the list. It will be filled up later only, right? Because
Can
S1
you
is not
explain
even
that with
evaluated.
the pointer
Yeah.
notation?
We will take an example and then we'll explain.
Yes, ma'am.
Yeah. All of you make a note of this. Take the same example which we had used. We need all these things because we have to refer this, okay? Otherwise, you will not understand how it is giving the labels. All of you write the syntax tree for this. Or x greater than 200 and x not equal to y. Okay. The main example, if of this is equal to x is equal to 0. But now we are there in the evaluation of Boolean expression. So the tree should be constructed for this Boolean expression. So how will you write the instruction? The tree for this.
Or will be the root.
Right, first parenthesis. Then you will see, okay, or is there? You have this x less than 100. The less than is having higher priority than or, so I have to create this on the left hand side of the or, and the right hand side of the or should have all these things. And will be the root for this. To the left, you should have x greater than 200. To the right, you should have x not equal to y. I see a lot of people are making mistakes in creating the syntax tree itself. So B1 or M B2. Okay, I have taken this. B1 or MB2. Now B1 is again composed of, I will just write E1, relational operator, E2. Okay, then now M is there. We will give the attributes later. Let us construct the tree first. B2 you have, then you have this one, B1 and M B2. Okay, B1 is again having x greater than 200, x not equal to y. Any dots here? Okay. Now at each of the nodes, okay. So B1 and B2 are nothing but B's only, right? So I will just remove the numbers here, so that later you will not worry that how that B came into picture. So at every node, I need to have the true list and the false list to be evaluated, right? So if I have to evaluate the B dot true list and B dot false list, at this particular node, I need to have the list being generated for B and this B, isn't it? So now if I go with the depth first search order, I will have to go like this, right? So I have to evaluate the B dot true list and B dot false list here, right? Suppose the index to which, or it is becoming congested, I will just write T and F. Is that okay? T is true list, F is false list here. Okay. Now you tell me at B dot T, how do I create the true list and false list here at this particular node? Refer to E1 or E2 relational operator semantic group. What we have there? We create true list and the false list, right? E1 relational operator E2. Refer to that. B dot true list is equal to make list we call and we pass the index. Instruction. Then next instruction, B dot false list, make list is my next instruction plus 1 we do. So if I start with the list 100, what will be B dot false list? The index. If I start next instruction, because it is some index number, so you can start with 1 also, not a problem. I've started with 100, some random number. What will be b dot false list? It will be next instruction plus 1. Isn't it? Did you understand this? Because when I come to this b is again composed of x less than 100. That is even relational operator E2. So that semantic action for this, when even relational operator E2 is getting reduced to b, it will get generated b dot true list, b dot false list, emit and emit. All of them will get generated. So emit, I have, this is the true list index. So I have if x less than 100, go to blank. Okay, at 101 it is the false list, so it will be go to false list. Okay, understood? Yes, no. Huh. Now we have come like this. Or is there? Then when it comes to m, okay, m, I have the production. What is that? Is epsilon, right? Now this is getting, epsilon is getting reduced to m. So what is there? M dot instruction. I will refer to I. Okay, is equal to next instruction. The next instruction to be what? It should be the address of the next instruction which has to be executed. Now, if this is B1 and the whole thing is B2, again in B2 I have B1 and B2. So when it jumps from B1, now I have completed B1. Now M should have which address here? Okay, let it be. It's fine. Now I have to have B dot true and B dot false here. Now you tell me the index here. Because when I traverse here, it will come here, right? I have to just put the address here. Let us wait for that. Now 101 I have stopped the index. What is the next one? B dot true. I cannot use 101, right? Because it's already the false list of this B. So I will use 102 and B dot false list will be 102 plus 1. That is 103. Okay? Understood? Now what will be the M dot I? What should be the index to which I have to jump to?
That last x dot.
So M dot I should have next instruction. Next instruction at B is nothing but 102 because B dot false is next instruction plus 1. So when it is it has completed B dot true list and B dot false list at this particular node, then it has to jump to x less than 200. That is B dot true list first because it is next instruction. This is next instruction plus 1. And at M gives epsilon, we have M dot instruction is equal to next instruction. Right? Remember, this is not a list, it is the index. Okay, list is denoted by this flower brackets. This is just the index of the next instruction. Right? Now, when it completes this and is done, it comes again to M. At epsilon, again we need to have M dot I. Okay, now you tell me. Now it comes here. When it is reducing, again true list and false list should be created. 103 is the last index which we have used. So I will use 104 true list. False list is 104 plus 1. That is 105. Now you tell me M dot I should have which number? Once it completes the execution of this, what is the next instruction?
104.
Yes, it is 104. This is the next instruction wherein it should start the execution. Right? The target of the jump should be 104 here. Okay. Now, next, once this is done, when it is reducing to this B, true list and the false list, you have to tell me. Look at the, okay, we didn't write 1 or 2, and here 1 or 2 will have what? What 1 or 2 will have? The true list, right? If x greater than 200, go to, this is the true case. 103, it will be, go to, this is the first case, the even relational operator E2. We just created this list and we didn't write this. At 104, again, it is the true list. So if x not equal to y, go to, this is the true case, and 105, it should be the false case. Now all the jumps are left blank. When it is reducing B and B to B, that time you have the backpatching being called. Okay, what do you have? B gives B1 and B2. Backpatch B1 true list, comma M instruction. So B1 true list is what? B1 true list is 1 or 2. M instruction is 1 or 2. So this true list should be backpatched with 1 or 2. Where do you have this B dot true list? Okay, backpatch will do it later. Let us evaluate the true lists first. What is B dot true list? What is B dot true list? And B gives B1 and MB2. B dot true list is B2 dot true list. What is B2 dot true list? Refer the semantic rules.
104.
104. What is B dot false list? It is the merge of
B1 dot false list and B2 dot false.
list
False.
referred to as 103 and 105, right? So likewise, you try to write for this. I'll take the attendance by then. You have to tell me the index is there.